Hello and welcome. Today we will be presenting our research in geometric methods in computer vision. I'm Brooke.
I'm Jose.
I'm Ian.
I'm Alex.
And we would like to thank our mentors, NC State and the NSA, for making this possible. Motivated by applications in automated assembly, handwriting recognition, and classification of arm movements, we studied what makes objects congruent. We studied specifically what transformations define congruence in the special Euclidean group and the equiaffine group. The special Euclidean group uses rotations and translations. You can see the red and blue triangles are congruent under the special Euclidean group. The equiaffine group defines congruence with an area-preserving linear transformation matrix and translations. All three triangles at the bottom are congruent with respect to the equiaffine group because they have the same area. Within these groups, we studied curvatures since curvatures do not change under transformations. Invariants in the Euclidean and equiaffine cases lead to the reconstruction of the curve from curvature. In the table, the first row shows the group's respective arc length parameterizations. The following row shows the relationship between parameterized curvatures and gamma. The last two equations allow for the reconstruction of gamma. For the Euclidean case, the tangent vector can be reconstructed with a first-order ordinary differential equation relatively easily. Then it can be integrated to find gamma. Our main focus is on the equiaffine case. The second-order ordinary differential equation to find the tangent vector is more difficult to solve. But after solving, the curve can still be found by integrating the tangent vector. We have used the power series reconstruction method to solve this equation. Each component in the equation T double prime is mu of alpha T can be represented through a power series as long as mu of alpha is analytic. Through substitution of these series into the equation, you can solve for the individual B sub n terms in the series solution to T. That solution can be integrated to find gamma. Next. And here are curves that have been reconstructed for their different curvatures.
Right. So in some scenarios, your curves may not be analytic. They might just be smooth. Your curvatures may not be, that is. So we like to use this tool called the Picard iteration. Now, what a Picard iteration does is that it'll take your curvature, and it'll create a sequence of curves that'll converge to the curve that you have as a solution for that curvature, for your associated equiaffine differential equation. So what this is doing is that you first have to decide on some initial condition. And this initial condition will just tell you how your curve is being oriented with regards to the point where it's starting. So what we have over here is that we have 20 iterations of curvature -1, and what ends up popping out is simply your curve is a circle. And you can see that as the iterations increase, they will converge to that circle. So as you continue to iterate, you see here for curves gamma 1, gamma 6, gamma 12, gamma 18, that just refers to the number of iterations you have up until that point. And what the iterations in this case are doing is that it's allowing you to plot your curve in a longer interval of convergence. So for example, in gamma 1, you really only approximate a circle for the first few angles of that circle. But once you get to gamma 18, you see that you approximate that circle on the whole interval that you take the angles of that circle.
Now, so far, we've only talked about this idea of curvature, which is a differential invariant, or something that will be the same no matter how we change our curve by whatever group action we're acting on. That is, it could be the Euclidean group where you rotate or translate your curve, or other more complex groups like the equiaffine. One thing we want, though, is something that will be easy to check whether it's the same no matter which curve we look at, and that brings us to this idea of a signature. That is where you take the curvature, but then you also take the derivative of the curvature, and then you put these together to make a parametric curve. Now, this set of points will be something that is the same regardless of how you act by your group, And so you can think of it as somewhat of a thumbprint of your group. It's going to be some identifier of whether you're in the same family of curves. One thing we really wanted to verify about this object is that it's robust to small deviations. If you're working in some real applied scenario, you'll never be able to find exactly the signature. You'll always be estimating it. So we want to be assured that even if it's slightly different than the true signature, the curves will more or less be the same. So what does it mean to be more or less the same? We have to make that a more formal mathematical notion. And that brings us to this idea of a Hausdorff metric. What you want to do is look at all the points in your two curves, or just two objects, and then at each point you want to find the closest point in the opposite object, and then you want to find the longest of these closest distances. So if you look here at this green and orange ellipse, when we restrict them to these different blue regions, we're able to find these longest, shortest distances, and then it grows as we take longer or bigger and bigger regions. So the key intuition for our argument for why this is a robust measure is this idea of the signature as a phase portrait. That is, because it's the curvature and the curvature's derivative, the location of this curve in the plane gives us the exact way that the curvature is changing and its values at each time. Thus, when we take two signatures that are close enough together, we can combine them into some nice region, as shown here, and the top of this region corresponds to the fastest traversal, and the bottom corresponds to the slowest traversal. And so we're able to gauge just how far apart our curvatures will be at each time, and from that we can see how far apart our curves will be using methods such as Picard iterations. Here we just have some examples where we take signatures and take them closer and closer together. Then on the right, you see that the curves themselves will become closer and closer together.
Right. Signature does have some weaknesses, though. And in particular, we're going to look at a weakness when you introduce periodic curvature. So we're going to start by with this idea of a bump function, which is a way to smoothly deform curvature. And we can use these bump functions to construct this sequence of curvatures, kappa sub n, such that the distance between kappa sub n and sine of s is less than or equal to pi over n for all s. So some properties of this particular kappa sub n that we've constructed: it's smooth, periodic, and it converges uniformly to sine of s. Since kappa is a periodic curvature, and so is sine, the signatures will be closed, meaning they'll loop. Right, so that's important later on. So here are some examples of kappa n. We have kappa 3 on the left and kappa 10 on the right. You can see that as n increases, kappa n gets closer to sine. Now let's introduce this idea of gamma sub kappa, which is the curve that we can reconstruct. Remember, this is special Euclidean curvature and special Euclidean reconstruction versus affine reconstruction. So gamma sub kappa is the curve reconstructed from curvature kappa s with these initial conditions. So here we have two examples of reconstruction. On the left, we have gamma sub sine, the curve reconstructed from curvature sine. And on the right, we have gamma sub kappa 3, the curve reconstructed from curvature kappa 3. You can see there's a big difference between the two. Most notably, gamma sub sine is an open curve, while gamma sub kappa 3 is closed. And in fact, in general, gamma sub kappa n will be a closed curve. Here are two more examples, gamma sub kappa 5 and gamma sub kappa 10. As you can see, they get bigger and bigger and bigger, but they are all still closed. And this goes back to that idea of the signature being closed, right? Because if you'll see, it's sort of tracing the signature more and more and more times in order to like carve out these curves. And the arc length interval that you're doing this over gets bigger and bigger. So in order to like look at closeness of curvature and conclude closeness of the curves we can reconstruct from curvature, you actually have to fix an interval on which the curvatures exist. So some further steps we can take is looking at like non-integer n, because these curves that we can reconstruct from kappa n are actually like pretty interesting and have unique properties. So that's the next direction that we plan to take with this idea of introducing bump functions to sine of s. We'd like to wrap up by thanking our mentors, Irina Kogan and Eric Geiger. And we'd like to thank the NSA for sponsoring this REU and the NCSU Department of Mathematics.